Okay, we're on the last video. Woo! Right, okay, now then let's have a look. So we were set up here and just been running some basic tests, and what I've set up here is, once again, I'm on your right hand side, and what you'll see on the screen here is the results of a, let's see, it's a 1:2 ratio, so this is going really fast, and we saw from the description of the previous video that we don't get any saturation. So you'll see here, this is a showing a the gain of 1 on the result that feeds into the actual limiter software before it goes into the servo, and this isn't saturating, therefore by the with the anti-feedback software, it doesn't take any effect, and therefore this is not going to make any difference. Now we haven't actually run this. I've got the Ka value at 0 at the moment, so it wouldn't run any anti Windup software anyway, because our Ka value is 0. But just to prove to you that if I do put a Ka value in, it doesn't make a blind bit of difference to how the system performs. So we've got it set up, as I said, for a 1:2 ratio. It's a high-speed version, and there's our error signal from the compass coming in, which is on channel 1 over here. And similarly, this is the total result coming out of here on channel 4. And that's really the only two parts we're sort of like really interested that we can actually relate to. It's been set up with the Ziegler-Nichols parameters. So for a 1:2 ratio, we've got an integration time of 336 milliseconds, and we've got a K value of 0.72. So that's what's been set up in this situation. And so I'm just going to run this. Now we're going to move the compass to the south by using option 10. So there we go. And then I'm going to hold on to this and then run option number 1, and there you can see the response time. Now then, if there's no saturation, and also I've got the Ka value set to 0, so that's my anti-wind-up feedback constant. So even if I made that 10, which I'm going to do now by using option number 3, and I can make this 10, so it would multiply any error that's coming back that's from the saturation by a factor of 10. I'm going to move this compass south 10, and I'm now going to run the algorithm. Just hold on to this because of what it does, and then run it, and you can see it doesn't make a blind bit of difference. The change in direction here is only because of where it starts from. So when it overshoots, right when it gets to south, it may be on either one side of south or the other side of south. It depends on what side it's on, which direction it goes in, which is absolutely fine. That's exactly what it should do. So we're not seeing anything there. So let's see what happens when we actually put this onto a 1:1 ratio. So I'm just going to lean over here and take this off here, put that onto there. 1:1 ratio is here. Okay, so we're now on a 1:1 ratio. I'm now just going to change the parameters because from the Ziegler-Nichols formulas, the integration time should be 296 milliseconds, and the K value should be 2. So I'm just going to edit those parameters. So I'm going to change, taking option 2, I'm going to change that to the K value of 2, and the integration time, I'm going to put the integration time to 0 first. So option number 3 for the Ka, I'm going to make 0. So we got no feedback coming back from the anti-wind-up. And also I'm going to take option 4, which is my integration time, and I'm going to set that to 296 in accordance to the data that we extracted when we were doing previous tests, and this is in accordance to the Ziegler-Nichols algorithm. So let's enter that. I'm now going to move the compass to the south position, which already is, so it shouldn't really do a great deal. Oh, there, it's moved a little bit. Right. And then we're going to run the algorithm. And there we go, and that's pretty much what we saw on the screen when we were doing the description in the last video. In fact, it should be identical. So here we'll see flatlining on here, which means the DACs have saturated, which means the number's gone, in this case greater than 512. Which means that, in fact, also the servo, because interestingly enough, the range of the DAC is not dissimilar to the range of the servo offset, which is actually quite convenient. And so that's flatlined, and therefore we know that it's saturated. And so I'm going to apply a bit of gain onto this. Now remember, the anti-wind-up gain only takes effect during this period. So it's actually really not going to make that much difference to this algorithm at all. So let's actually take our Ka value. We're going to load in a factor of 10 now. So let's put in anti-wind-up Ka value. So it's option number 3. Going to increase that to 10. And now I'm going to put the compass back to the south position. And I'm going to run the algorithm again. And just look at this point here to see what happens. And at the moment it's around about 1 division wide. If I just look at that flat line there is about 1 division wide. Let's just see what happens. So, and you'll now notice that it's actually flattened it off. And so now it doesn't matter how big I make that. So 10 has improved it slightly. So the chances are it's actually made the response time just a little bit faster because it hasn't had to get rid of this extra data in the integrator. So it's made it slightly faster, but not significantly, because it's actually quite a small overshoot from the, or it's a quite small saturation in comparison to what we're about to experience when we run this on a 2 to let's see, a 1 to 2, sorry, a 2 to 1 ratio, which is a very, very slow process. And this is where we see it at its best. Okay. Now, obviously, when we are running this as a normal control system, this doesn't make any difference to the algorithm because we're not getting into saturation anyway. So the whole purpose of the anti-wind-up is actually the scenario which we discussed in a couple of videos ago, which was what happens when you've got a system which has actually got an extreme starting point, like all of a sudden there's a massive change, and that's when anti-wind-up really comes into its own, because it means that the system actually stabilizes much more quickly. But in this case where we're just wandering this around, this is just working as it should because the anti-wind-up isn't coming into effect and therefore it has no play in the system. So let's exit this. And now let's put this onto our worst case scenario in the case of anti-wind-up, and we're now going to make this go really slowly. Right. So let me, I just need to change the values for the constants. So I'm going to, as per our pulley ratio 2 to 1, and looking at the data associated with this from the Ziegler-Nichols formula, we're now going to put in option number 2, where the constant's now 4.4 as per Ziegler-Nichols, and the integration time is still 296, which is absolutely fantastic, so that's great. And I'm going to turn the anti-wind-up off first, so the anti-wind-up constant I'm going to make to 0, so there is no anti-wind-up at the moment, and we can run it and then do a comparative result. We're going to move the compass to the south position. There we go. Okay, and now we're going to run the, oh sorry, you've got to stop that. That's because of a small bug in my software. I'm just going to change this. We're going to move it back to south again. There we go, and I'm just going to go to 1 and move this around slightly and run that again. Right, there we go. So I'm going to close the time base down on this because we need to see it in a bit more detail. So I'm just closing that time base down and offsetting the trigger signal. So let's go X from that algorithm, put it on to 10 to get back to our south position, which is fantastic. I'm just going to turn this a little bit, and I'm going to run the algorithm. Right, so that's what we saw in the last video from the slide perspective. We're on now 1 second per division. So it's taking approximately 2 seconds of this 2 seconds of saturation here, and then it's actually getting into its normal region, and there's about 1 second of saturation here, and then it's going into its normal region. So these 2 points here, this one and this one, are where the anti-windup's going to really take effect. Now at the moment the anti-windup's off, so let's just see what happens when we start to put anti-windup in. Now also note that this is quite happy as a control system, working normally because it's not saturating, but what's really bad is how long it takes to get to a start point from an extreme position. So that was taking what, 1, 2, 3, 4, 5, nearly 6 seconds to get back to a normal point from an extreme offset position. So what we're going to do now is exit that, and we're now going to go to our south position. All right, and I'm now going to add some anti-windup, and I'm going to put the anti-windup in as 5. So 3 is the option to do that. So I'm changing my Ka constant, and I'm going to put in 5. I'm entering that, and now I'm just going to make sure it's offset there, and we're going to run this. Now you'll notice, see the difference here? Much quicker. We haven't got such a long delay now, so the anti-windup's had a really big effect. Once again, the anti-windup has no effect on the general operation of the system, but the anti-windup has improved our start position enormously in comparison to what it was before, which is fantastic. So, and that's actually that's pretty good at 5. We've cut this down by to 1 second before for the first overshoot, and it's now down to 2.5 seconds from the original 5 seconds it took. So we've improved it by a factor of 2 in terms of the time it takes to get to its steady state from an extreme starting position. So let's exit from that, and now we're going to make the anti-windup 10, the gain Ka, so I'm choosing option 3. I'm going to make this 10 and enter that, move the compass to the south position. There we go. There we go. I'm just going to turn this slightly over here, just to get rid of the bug in my software. It's a bit of a pain, but anyway. And so now we're going to run the algorithm. Now look at this at the moment. We've got a 1 second, we're on 1 second per division. That's 1 second here of saturation. And let's just see whether it reduces that even more. So just watch this, because the scope is running really slowly. So you can actually see the difference between what was there and what is going to happen. So now let's see. And in fact, that hasn't actually made that much difference. So this would suggest that there's, once you get to a certain value, it doesn't actually really have any drastic effects. And that's primarily, if you look at where it starts to change, there's the point at which it gets to 0, where it starts to change the direction and starts subtracting, and that's actually working really quickly in terms of getting this down. So we haven't got much overshoot there, so it is actually doing what it should be doing. And let's just put an extreme value, let's put 100 in to see if it makes any difference. So we'll move the compass south again, and put the 3 is the K value. I'm going to change that to 100, and I'm going to just move that slightly, and then run the algorithm. Oh, and that's where I think there's actually a bug in my software with this, whether you get numbers that are actually too big. And it'd be interesting to actually simulate this to actually find out what's physically going on in the math, because that suggests that the whole thing has actually gone nuts. So so let's go back to the south position, because if that number is actually too big to begin with, then what happens is you actually may end up actually taking the maths way outside if it's normal limit. There's probably a problem with my math, and I probably need to put some checking software in there to make sure the numbers are not stupid. So I'm just going to bring that the k value to, let's put the k value back to 10. So I'm going to put 3 in, the k value of 10. Let's just put that there and run. There's our normal. So that was k again. And just exiting from that, I'm going to make the k 20 now. So I'm going to choose option 3 and put in 20. And now, let's see, go to the south position. All right, just going to move that around and then go run into 1. And we're on around about 1 second there. And once again, it doesn't seem to make a blind bit of difference. So it appears as though when you go to 10, let's just have a look at what happens when we go back to 5. So let's put it back onto 5. So let's go to south position, and Anti Windup will make 3. We'll put in this 5, and then we'll run the algorithm. So 5 is actually okay, so let's make it 2. And so KA is 3, change that to 2. And now move the compass to the south position. And we'll now run this. Run that with 1. Right, I was just thinking about this in terms of the values. If you think that this KA value is 2, you've got to remember that if there is a very large offset and it's in the hundreds, then that's a significant amount of data it's taking away from the actual error signal. So it's not surprised that these bigger numbers are actually causing problems and actually don't have an effect after a while. So I'm just going to make that constant 3. Let's bring that down to 1. And what I'm looking for is a change in here as I bring these numbers down to find out what point does it really start to have an effect. So let's move that to the south position. And let's run that again. So even with 1, that's still the same. Let's put in k is, let's go 3, and let's put that at 0.5. And move the compass to the south position. And run the algorithm again. Right, that's not having a massive effect there, so let's put it to 0.1. Whoops. Let's take the let's see, the 3, option number 3. We'll make that 0.1, and then move the compass to the south position, and then run the experiment again. Let's just move that around. Right, and that's where you're starting to see it extend. So we're right down at 0.1, so it's not taking much feedback to actually start to make a difference on this. And if I make that the KA 0. Let's say 0.01, and then move to the south position, and let's run 1, and now you can see it's really extending it, not far off. So the best performance we were getting was looking at around about 0.5. So let's put this back, and now let's look at the option number 3 at 0.5 is the KA value, and move this to the south position. And so we see here, this is taking 1, 2, 3, 4, 5 seconds to, that was at 0.01. Now we're at 0.5 KA. And now let's run the algorithm. and that's pretty good. That's improved it that's about 3 seconds to get stable, which is fantastic. It's a very good improvement. And let's now reduce it a little bit, increase it a little bit more. So let's make that to 0.7. So 3, 0.7, and we'll go to a south position. And then run the algorithm. So around about 1 and a bit seconds here. Let's just see if it's improved it. No. So that's changed to around about 0.5 is perfectly adequate to get this to work effectively. And now, once again, if I'm moving this around, this is not going to make a blind bit of difference because the Anti Windup is not taking effect. I'm going to put the scope onto normal trigger. There's on auto, and now you'll see as I'm moving this, you'll see the total error signal, and it's not saturating at all. Yes, and that's quite. And that's the way a system would normally operate. It very rarely goes from an extreme of one to the other, unless you're actually initializing the system. But that is actually showing you the actual error here, but there's no saturation. So that's pretty much it. I hope you've enjoyed this series of lectures. I haven't bored you to death, but this is what you would have done in your experiment. I'm going to make an introduction video now and a conclusion video to add to all of this. So that's when you'll see me next. Okay.